All right, everyone. So I guess I'm the only one who's going to talk about firms for this summer school. But I do think there's a lot of overlap between firm and individuals in the sense that there's always a very fundamental element that we're actually interested in. In terms of individuals, we're very interested in how their human capital production function looks like and how these things being formed. And in terms of firms, that's exactly the same. Usually the beginning point to think about firm is to think about how do we understand these firms are so different, right? So we've seen very successful firms. We've seen these firms that fail within 1 or 2 years. So this whole lecture is going to tell you about how do we just like a starting point, how do we measure and how do we model firm heterogeneity that you see in our economy. Okay, so I'm going to try to just start with a small motivation here in terms of did this work? Oh, this is plugged out. Okay, okay, I think it works now. Okay, so here I'm going to talk about how to estimate producer technology and measure the producer heterogeneity using micro-level data. This is always the first and one of the most important setup on model firm decisions, right? So once we know this, we can think about a lot more sophisticated decisions of the firms in terms of different type of investment, whether they should enter, whether they should exit, what kind of pricing strategy they have. But typically, the production decision is one of the first one we're interested in, and I try to understand. And it also has a very long tradition. It's very firmly grounded in the basic theory of production, right? So in terms of the kind of historical overview of what the literature will be looking like is that the first generation of these studies, they typically utilize industry or every level time series data. So that's back to the like 60s, 70s when we don't have very good micro level data collection effort. And then what the literature typically focus on is to say, okay, the world is very complicated. So let's actually focus on let's model the technological specification very flexibly. We want to have very flexible technology, but worry very little about what are the standard econometric problems related to these kind of flexibility assumptions, right? So basically, starting in the early 1980s, pioneered by Guangzhou and his co-authors, the later studies actually shift their attention to the micro-level panel data. And where, given that you have much more data, they start to pay much closer attention to the details of these econometric identification problem and the estimation problem. So basically, this will be our starting point today. And then I'm going to talk about two separate literature that has developed from this Guangzhou's earlier work. Okay, so Guangzhou has some framework, He's one of the giants in this literature. He basically is very forward-looking and point out a lot of the different directions that literature could be going. And here I'm going to talk about the two most common approaches that has been usually utilized in the literature. One is the dynamic panel, and the other one is the control function approach. Okay, and if you look at the more recent literature in the last 5 to 10 years, we also start to see there's a convergence of these two kind of approaches over time, and people now start to rely on the insights from both. So I'm going to give you some examples here. Okay. So by the way, feel free to raise your hand and ask questions. Any type of question, or just let me know. If it's too easy. You've already seen this. Just feel free to say it, and then we're gonna skip some of the content. Okay. Is that good? Okay. All right. Okay. So let me just show you a few production functions, right? That's the starting point, okay? The first one everyone should possibly know, right? You have already seen. This is what we call the Cobb-Douglas production function. And this is very commonly used in both macro, in both international trade or any of the kind of micro level production function estimation. That's usually where we start with. A slightly more complicated one is what we call the CES, right? So that's a constant assisted substitution production function. You will also tend to see in a lot of literature about when we start to talk about technological bias or like factor bias, and things will get much richer there. the reason it's called CES is obviously, that's coming from this idea that the elasticity of substitution between the two input factors of capital and labor turns out to be a constant, right? So that, although the CES is actually more general than the Cobb-Douglas, because Cobb-Douglas is actually going to be a special case of the CES production function. Okay, I'm just going to show you a simple algebra here. Basically, what you do is like you take the L'Hopital's rule and making this gamma goes to 0, and basically what you can show is that the CES is going to converge to a Cobb-Douglas production function, where the Cobb-Douglas coefficient will be just the relative magnitude of these two coefficients in front of these two factors. Okay, is that clear? Okay, so now CS is a little bit more general. Why is it being used less? I mean, it's partially because in earlier days, the computer is not that powerful. And then, if you take logs of a Cobb-Douglas from the left-hand side and the right-hand side, it becomes a linear equation. Okay, the linear equation is very easy to estimate and very easy to implement. But if you look at CS, it will be a nonlinear equation, and it usually takes the more like optimization problem, and just people get lazy and they say, okay, why don't we just stay with Cobb-Douglas? Okay, so that's the, but that's attracting more attention now, and maybe if I can summarize later, there's a certain literature, especially when you start to worry about bias technical change, you'll possibly have to rely on CS. Okay. And then there's a third class of production function, which has been used to be very popular in the earlier literature when I talk about people kind of care about flexibility, but now kind of like got forgotten and kind of rediscovered. That's the whole academic research. Sometimes you have knowledge being forgotten and discovered, and after like 20, 30 years. So this is what we call the translog. The translog, if you only focus on the first three terms, looks very much just like a Cobb-Douglas, but then you have these like high order terms and end up there. This kind of like a second order term, and also have these like interaction term. Again, this is another generalization of Cobb-Douglas with more flexible elasticity of substitution. Okay, so in some sense, you can think about it's even more general than CES, because in CS, despite the fact that it's being more flexible than Cobb-Douglas, it doesn't allow for the elasticity substitution across capital and labor to vary with the firm size. Okay, and then sometimes we think about that's not that realistic, right? So if you want these elasticity substitution, especially the output elasticity of certain factors, to vary across firm size, you might want to stay with a translog production function. And the other attractive feature of the translog is that if you look at this, it looks a lot like a polynomial approximation, right? Second order polynomial approximation. So what does that mean? That means basically it can be understood as one of like these approximation production function, right? So as long as the true production function were twice continuously indifferentiable, then this will be approximation for this kind of production function, whatever you will be approximating for, right? So if you think about the world is too complicated, we have to approximate the true production function, this might be a good option too. So, but then, why this is not so commonly used in macro literature, in trade, the reason is because that production function is not that convenient for aggregation purposes. Okay, so if you think about this production function, these high order terms, especially the interaction terms, if you're a micro researcher, you will find this very attractive and very flexible. But if you try to build that up, what does the industry production function looks like? What does the aggregate production looks like? This will be pretty hard, cumbersome to work with. That's the reason a lot of the trade literature stay with CES, macro literature possibly with like Cobb-Douglas. But if you're really serious about using micro data and estimating production technology for the firm, maybe this is something you can also get started with. Okay, so that's the basic introduction of like three types of things that we're typically going to start to see and actually work with in this literature. The other important thing I want to point out here is if you look at all these three production functions, they share a common feature, which is what this AI. Okay, so what do we usually think about this AI? So this AI is in the early language we call this productivity, or call this total factor productivity, which literally is something that's not known. Okay, so basically the idea is that we see the firms being inputting the same amount of capital, the same amount of labor, and somehow miraculously some firm actually produce a lot more than the other one. So okay, so how do we try to explain it? So all the unknown things that's been explaining the heterogeneity across firm being loaded on this AI. Okay, so a lot of the work that in this literature is trying to say, can we actually microfound the difference of this AI for these firms? Okay, can we actually try to interpret that from some observables? And can we understand how firms' decision to improve these AIs? Okay, one of the things that I want to point out here is that the way that AI enters all three production functions I laid out here, it's actually going to affect each factor equally. Okay, that feature is going to be called a factor neutral production function. Okay, so far in these applications, like in this literature, like 90% of literature being focused on factor neutral production functions. So we'll be starting from there. But again, it's useful to point out here is that you not necessarily need to think about the AI must be factor neutral, right? You can easily think about maybe for some economies that the technology that's been affecting the capital is a lot more quick, fast moving, because of the quick reduction of the capital prices. Or in some economy, maybe because of the quick accumulation of human capital, there's like labor augmenting productive change. So you can get a lot richer than that. But just for now, let's think about AI just being what we call total factor. Okay, so this is factor neutral here. Okay, is that quick questions? No? Okay. Okay, now I'm going to give you a very easy example and just make you to use your undergraduate econometrics training to tell me, what's going on, right? So here, a Cobb-Douglas example, right? So think about we stay with Cobb-Douglas, and I'm going to estimate a production function like this, okay? So basically, I'm taking logs of the production function, right? The left-hand side will be the log output. The right-hand side will be the log input. And then you have the epsilon I, which is basically just we transform the log AI into a constant term beta, which is exactly the same across all firms, and the epsilon I will be different across the firms. Okay, so if we call AI log TFP and it's typically unobserved, right? So the question for you here is that if we estimate this equation using ORS, will that work to actually tell us exactly the right coefficient for this Cobb-Douglas production function? Okay, I give you 5 seconds to take a stab at it. If yes or if no, what's the problem? Yeah. Okay. So what's the reason for that? Why do you think there's a power dispersion between it?
Firms will tend to hire more employees to produce.
Okay, that's great. No wonder you guys are the best out of your own university. Okay, so there's a actually I should reveal the answer too quickly. Actually, there's another reason. Anyway, so I'm going to tell you. The first reason is exactly as you correctly pointed out, right? If we think about the firms being maximizing its profit, and if you think about just in a very simple word, firms gonna take the output price and the input price as given. Sometimes this doesn't hold. We will actually talk about this later. Even in this case, what's going on is that the optimal labor choice, right, will be exactly a function of the productivity, right? Which means that the Li is actually correlated with epsilon I. That's the simple like econometrics 101. And then this is what we typically call the simultaneity or endogeneity bias, right? In terms of the and typically because this is going to respond positively to epsilon I, you tend to see the beta will be having some upward bias, right? Okay, so I'm going to now also talk about the less appreciated, but if you work with data, you will always pay attention to this kind of problem. You always notice that there's a second problem which is embedded in this Ki. Okay, so typically what we think about is that the Ki, which is a capital stock, it's not going to be that quick moving. So maybe it's less subject to this concern about simultaneity bias, right? If I have a good productivity shock, the quickest I'm going to build another building will be like 5 years from now. So maybe it's not that problematic. But the big problem in Ki is that there's this measurement error in the inputs, right? So just as an example, if you look around the room, I will ask you how many people are in this room. You possibly will actually do a pretty good job, right? If I give you 5 minutes. If you look around this room, I say how much capital do we have in this room? if I give you 15 minutes possibly you won't be able to tell me, what the value of that is, right? So that's show you how hard it is to actually measure physical capital in a kind of manufacturing plants, right? There are a lot of heterogeneity in these different capital machinery, and typically we would believe that the capital stock is actually mismeasured, right? So given that, what's going on is that the Ki actually, instead of like simultaneity bias, what's going to subject to is this kind of typical what we call attenuation bias, right? So if we have a classical measurement error problem, what you have is that you're going to cause the coefficient before capital to bias downward. Or downward meaning that downward close to be zero, right? So that's the two standard problem of OLS estimation of a production function would be actually looking like. Okay, is that clear? Okay, so these seems like pretty simple problems. But turns out it takes generations of researchers to actually overcome of them. In fact, even just yesterday we had a half day, people coming up with new strategies to kind of tackle this kind of like production function estimation problems. Okay, so if you were a researcher, if you're looking at this problem, what's your first reaction? What's the typical tool that we use to kind of tackle endogeneity econometric problems? Yes, exactly. Yeah, IV. No, isn't that straightforward? And always look for IV. But generation of people have been looking for IV and not that successfully. The reason is I think I jumped ahead of myself. Okay, let me talk about this before we go to IV. Okay, so there's one thing I want to tell you about, which is possibly well known, but less appreciated also in the literature. Okay, so this is one specific feature I think the production data typically has, which is like we'll have the panel data, right? So panel data meaning what? You see a firm, and these firms you see this firm repeatedly over time, all right? So which means that you might be able to play some trick about the timing, right? So you can basically looking at if you see these firms multiple periods, I might do a first differencing. Everyone knows what first differencing is? Is that fine? Okay. So we'll do a first differencing is that you're saying, okay, I'm looking at output this period and look at output last period. Let me take a difference of that, and let me also look at the input for this period and last period. I'm taking a difference. And the same here, right? So, so this is typically the first reaction is that if we think about firms' productivity is actually relatively stable over time. There's not much shock to this productivity over time. Think about a pretty mature industry, or think about firm success is pretty primarily determined by this entrepreneur. If we think about each firm has Steve Jobs, can be totally successful, and each firm has something like me, would be totally unsuccessful, right? So that's just embedded in individuals, right? So if you think about this is pretty much constant over time, then by doing this kind of first differencing, you might say, hey, problem solved. It's at least for simultaneity bias, right? We can actually difference out this unobserved productivity term omega I. Is that clear? Okay. All right. So this will actually introduce another challenge, which is relatively well known for the Ki. Okay. So this is something you should bear in mind because this fact will be really useful when we try to explain some of the future generations of the estimation methodology here. The important thing here is that if you actually look at the difference between these two KIT and the KIT minus 1, and if you think about what is going to be the measurement error bias once we take the first difference of these two measures, which both are measured with error, okay, and if this error itself actually has some persistence, and this true variable of capital has some persistence over time, then this formula is very well known. Okay, it's been shown by Gritikis together with maybe Hausman in the mid 1980s. What you can be showing is that if if the true value of this beta k is actually this one, right? And if the measurement error has a standard deviation of sigma u square, that's the variance of measurement error, and the true capital has a variance of sigma k star, okay, what's going to determine the bias of this beta in OLS setup will be just the relative magnitude of the true variance with respect to the true variance plus the measurement errors variance. Okay, that's very intuitive result. That's usually going to happen. But once you take the first difference, you have to pre-multiply. You have to multiply this sigma u square with this additional term. This additional term is going to be the 1 minus rho u divided by 1 minus rho k star. Okay. So what does these two mean? This means this is the persistence of the measurement error, and this is the persistence of the true value of capital. Okay. All right. So now by staring at this formula and get rid of this one, this will be OLS, right? But if you look at this formula, what's going to happen is that this rho k star, which is the persistent of the true value of capital, right? So do you think this will be very high or very low? As I already said, capital is very slow moving, right? So this will be very high. If you look at this year's capital in this room, compared with next year, maybe they upgrade the computer a little bit, but mostly it'll be very similar. So what you have is that this is very close to B1, okay? The fact that this is very close to B1 essentially blow up this whole term at the denominator, right? So the fact that you blow this up whole term, which means that you pretty much get a very much screwed up estimator of this beta under the measurement error. So this is what with a well-known result that if you know that your capital stock is being measured with error, right, and then you try to do whatever like first differencing or fixed effect estimator, what's going to imply is that the measurement error embedded in this capital is going to be exacerbated. Okay, and this is a very well-known result. In early studies, and a lot of generation researchers run these fixed effect regressions. What they typically find is that, that's very weird, right? At the macro level, we typically believe that we have a roughly constant return to scale. Why at the micro level we have such low return to scale? And typically they have beta k plus beta o way less than 1. Okay, and then when they look at this more closely, what they typically find is that they have a beta k very, very close to B1. Oh, sorry, very, very close to B0. Right, so that basically tells you that this beta k is really confounded by these kind of exacerbation of the measurement error problems. Okay, so that kind of argument rules out a very popular class of estimators, including the first differencing estimator and the fixed effect estimator, in terms of resolving the simultaneity problem of these L's. Okay, all right, questions? Okay. So let me then back to another question. It's just like we were talking about. Now let's think about the second method. We were actually discussing about instrumental variables, right? Okay. First of all, ignore the measurement error, right? This is gonna complicate our life so much. Okay. Even you forget about the measurement error. The argument is that it will be also pretty hard to look for the right instrument for the labor. Okay, what's the reason for that? Let's just again look at this specific equation. Okay, again, tell me your econometrics 101 knowledge. What should an instrumental variable satisfy here? Since we're instrumenting for epsilon I, right? So what are the basic requirements for that instrument? Any take on that? In general, you want this not uncorrelated with the epsilon I, right? That's the first requirement, right? Okay. The second thing, you want it to be relevant, right? It should be changing your labor choices, right? Okay. So stare at this equation 2. What are the potential instruments you could potentially be using? First of all, we don't. Yeah, so let's think about relevance, right? So what are the instruments typically people have been thinking about using? That's these two pieces, right? This if it varies across firm, of course. usually people would think about, if you want to vary these input choices, you want to think about just factor prices, right? The WI. Maybe, don't we see different firms being kind of paying different wages, right? Can we actually use them as instruments? Yeah, if you say that yes, you possibly will fail this whole week, right? That's we all talk about labor and human capital and how do actually affect the efficiency of the firm, right? Okay, so there are a few very well-known reasons why actually individual factor prices is very hard to serve as instrument in strategies. In particular, you think about there are a few very well-known reasons. First of all, they might actually measure the unobservable human capital from individual workers, right? Which in turn will be correlated with firm productivity anyway. The second reason is that maybe the firms actually also have some market power, right? And then in that case, the firms of different productivity might also be having different market powers in both output and input markets, right? These are the standard concerns. Basically, rules out using the factor prices as the instrumental variable for the LI, right? Unless I'll have to make a few exceptions, right? Unless you feel that most of these variations of the firm level input prices being driven by certain reasons that the firm itself cannot control, right? So if there's some kind of I don't know a few good examples. Maybe just let me take like a reasonable good example is that think about the wages being regulated in some way, right? So then you think about firms cannot decide freely on how much the wage it's actually being paying to its workers. So it's being regulated in a certain way. Then maybe you could think about this as more plausible variations, right? But in standard cases, right, firms itself can decide on both the quantity and the quality of the labor force you'll be hiring. So the factor prices actually is not going to be that useful. Okay, so that makes the search for instrumental variable strategy also very hard. Okay, so basically what I did is, in a very quick speed, I kind of rule out the standard, just like if you read the Woodridge textbook, right, the standard procedure, like the first few chapters, instrumental variable, or the standard fixed effect, first differencing method actually do not work in estimating even such a simple production function. Okay, so now what can we do? Here are the two things that we could potentially do. So I'm going to first tell you about an easy method, okay, a little bit more ad hoc, less rigor, but it's pretty widely used. And I'm going to tell you also about a lot more model-based method. Okay, so the first method, as I said, I'm going to tell you is about the dynamic panel. Okay, so this is a pretty much started in the early 90s, but this paper actually summarized that pretty well. This is a paper by Blondell and Bond. Okay, what they do is they basically lay out a production function which has the following specification. Okay, so what you have here is actually pretty. What you have here is actually quite general. Okay, in the error terms. Okay, so we have the standard inputs of labor and capital, and you allow the productivity to change by this gamma t. But meanwhile, you also have this omega I, which is the same that we allow for in the first differencing and fixed effect model. Right? Think about this as some kind of entrepreneur or some kind of firm specific managerial talents embedded in this firm that's going to make this firm good and bad. Okay, and this VIT is going to be is actually going to be the what we call the transitory shock. These shocks can have a lot of explanations, right? You can think about maybe 1 year a firm is lucky enough to get a big order from a foreign customer, or maybe there's 1 year the firm is actually start to adopt a new technology, and a lot of things that as long as time varying but persistent, you will put that into the VIT. Okay, so the VIT in this model is going to be modeled as the AR1. Okay, keep that at the back of your mind, because later we're going to use this to contrast the next method we'll be talking about. There are a lot of differences across these two methods of estimating productivity, but one of the fundamental differences is that what kind of process you put in here, right? So here we're putting in a pretty general general process, which is going to be a fixed, unobserved, permanent unobservable, which is omega I, and also an AR1 process, which is the VIT. And the third term will be a term, what do we call the measurement error term, or maybe just like ID error term, which is the MIT. Okay, MIT is ID over time. Okay, so what's their first step in terms of working on this? In terms of working on this model? What the first step that they have been looking at is to substitute away this VIT. Okay, so this is a standard strategy. Okay, if you have this is strategy actually comes back from to kind of when you think about estimating time series models, right? If you have a simple AR1 process, what you tend to do is to kind of use the previous realization of these outputs and inputs and substitute them into the current equation so that you don't need to handle these unobserved VIT and VIT minus 1 anymore. Is that clear? Okay, I hope this is not confusing going from here to here. From this equation 6 to this equation 7, what we simply did was to write the VIT. Let me actually write it here. What we simply did was to say the VIT equal to rho VIT minus 1 plus FEIT, right? So what you do is to substitute in the previous realization. So this will be just YIT minus 1, right? Minus beta 0 minus beta LIT minus 1 minus beta K, KIT minus 1, gamma T minus 1, right? Minus omega I minus MIT minus 1, right? Plus EIT, right? Is that clear? So this is a middle step. Then I basically substitute this middle step into the VIT here, and that will give me this equation. Okay. All right. So so given this given this equation, now we're back to the original, almost back to the original challenge, which is we still leave the omega I in here, and then we're still worried about the fact that these inputs, especially the LIT and LIT minus 1, will be correlated with this omega I, right? We never, it just substitutes away the AI1. It doesn't really resolve the original challenge. It's still there. It's clear? Okay. And then we are still having this problem of measurement error, right? We didn't get that resolved either. This step is basically just simply substitute away the richer error structure. So it doesn't really do much in terms of helping with the original two problems that we talk about. Okay. Now we're going to tackle these two problems directly. Okay. So the first step turns out to be very similar to the first differencing and the fixed effect strategy, which is we're gonna first handle the omega I. Okay. We're gonna first take care of this guy. Okay. So what we'll be doing is just to take a first difference. Okay. That's what we did. We're gonna first do our first difference. That's just a first differencing equation from equation 7. When I take a first difference, that will give me equation 8, right? Okay, clear? Okay, okay. We got rid of that guy, but again, we still have problem. Okay, so the problem here is going to be the problem will be 2. Okay, still will be 2. We got rid of the permanent thing, right? First of all, we know that the EIT is the realization of the current productivity shock, right? So these are the ones that I talk about. Maybe something that happened this period. It's not permanent, but it's actually there are actually new things coming to you every period, right? And you don't rule out that the fact that maybe the firm's inputs, like labor choice, are going to still responding to this change of EIT, right? So this will still be an endogeneity problem. The second one is we still have the measurement error here, okay? All right, so what does this dynamic panel approach actually rely on? What they rely on is actually something what we call the sequential exogeneity, okay? So this is a very key restriction that they put on to estimate this type of models, okay? So the idea here is that, yeah, it's true that the EIT is actually going to be correlated with your choice, but this one is actually this one is ID over time, right? Just by the if you look at here, right? This is the L1, but the EIT is ID over time, right? So it's true that there will be contemporaneous correlation, but what the assumption we try to make is that whatever happens before this period will be uncorrelated with this EIT. Is that clear? Okay. So basically, any inputs, or including outputs, which happens before this period, we can potentially use them as instrumental variables to actually instrument for this endogeneity problem. Okay, that's the basic idea of this sequential exogeneity assumption. Okay, and the same applies to these MIT, right? If you believe these measurement errors are also ID over time, then you can make the same argument to use those variables as your instrumental variables. Okay, so again, now you can see the trade-off, right? The trade-off is that these kind of exclusive restrictions, they don't seem to be very model-based. Okay, there's no clear decision problem embedded at the back of these assumptions, right? On the other hand, it's pretty flexible. Okay, it doesn't really impose much. All it needs is that all what it requires is that there's these inputs actually are persistent over time, right? And these outputs actually persistent over time. Then you can use a lag value as the IV strategy for these ones. Okay, so that's the method they pretty much propose. Of course, there are few related to this equation. There's actually a few details, right? So, for instance, if you look at this equation, if I want to instrument for the change of the labor, okay, how many lags do we actually need? We need to use lag labor, right? How many lags do we actually need? Turns out we need 3 lags, right? So what's the key constraint for this lag? Is that this term is MIT minus 1 minus MIT minus 2, right? So anything that happens for that period, we cannot use it. So we have to use one more lag before, so which means you have T minus 3, okay? So essentially, basically what they propose is that they use all the highly lagged inputs and outputs as instrumental variable to estimate this linear equation. Okay, all right. So the moment condition is basically these IVs actually uncorrelate with these error terms. So you can embed this into a general method of moments framework and just estimate this model. Okay, all right. So in addition to this downside that I'm saying, there's not much like micro foundation for this. For this kind of like assumption in terms of how much the lag value correlated with your current value. There's another problem with this kind of approach. Which is related to the fact that you need far lag variables used as your instrument. So what are the potential problems here? The problem is that by using 3 or more lags, what you need is this firm will at least survive for how many years? It will have at least survive for 4 years, 3 or 4 years, right? So depends on how many lags you'll be using. Okay, so that comes back to another question. Like who are the firms that are going to survive for 4 years? Good firms, all right? So then what kind of problem we actually introduce here? Exactly. We kind of using the lag value to kind of use them as our instruments, right? We think we're good. These are kind of getting them to be uncorrelated with the change of the productivity, but we're kind of introducing sample selection problem here, right? So we're going to only get the firms who are actually on a high trajectory of the changing of these of their productivities, right? We're not going to get a firm who actually had bad shots. They're going to just possibly select themselves out already anyway. So basically, by looking at this strategy, we really introduce the samples. So that's why, and what are cases you will think about this will be a good empirical strategy. This will be a good empirical strategy if you only care about a group of firms that are relatively stable and without much high turnover rate, right? If you have a long panel of firms, these are the large firms that do not have much high turnover rate. These are the group of firms maybe that's applicable for this type of data. That's why the early application, for instance, if you look at Bond and all these, like a lot of the other applications, they have been focusing on the firms that are listed in the stock market. Okay, so these are the firms that typically, you can think about, the exit probability is not very high. These are pretty mature, they're large enough that they suffer much less from these kind of sample selection problem. You don't want to apply them to kind of like small firms in developing countries, okay, which could typically suffer like 20–30% exit every year. Then you're gonna be then you basically just put yourself into a huge sample selection problem by limiting those ones who actually live up to 4 years, right? Okay, is that clear? Okay, so this is gonna be the first strategy. There's one more detail I think I might want to just talk briefly, which is what is the there's another problem here, which is less well known. There's a sample selection problem. The second one is that in a lot of cases, as I said, the change of the capital turns out to be very close to be zero in a lot of firms. Okay, that comes from this fact that in a lot of the firms, or in particular, think about manufacturing plants, right? A very well-known fact is that they don't really move their capital every year. Okay, they do that like very infrequently. Some of them actually, after a few years, they actually have a big spike of they buy a whole batch of like production line. But on a year-by-year basis, the movement of these change of K is very small, almost close to zero. Okay. Then, when you come back to like instrumenting for this close to zero guy using a heavily lagged K, it's true that the heavily lagged K will not suffer from endogeneity problem. But again, the other thing people found is that using just strictly these moment condition is something what we call the weak instrument problem. Okay, so which is that it satisfies. It's not going to be correlated with these error terms, but again, it's not that correlated with the variable you want to identify either. So this kind of weak instrumental problem bothers these guys. So the earliest stage of the application of these methods, in addition to the sample selection issue, the weak instrument is also a problem that they try very hard to kind of overcome. Okay. So what kind of remedy did they come up with? Not that I do. Okay, it's pretty ad hoc, but but people start to use that anyway. So that's really the thing that you need to pay a little bit more attention to. Here, what they did is actually trying to say, these earlier, what do we call, first difference GMM. So this set of moments is what we call first difference GMM. Okay. So these first difference GMM actually have very poor finite sample properties. You apply them to a sample of like 500 firms, they tend to give you very bad like estimates everywhere, very noisy, mostly because of the weak instrumental problem. Okay, so what they did is that then they proposed a second set of moments, appending the original what we call the first difference GMM. So what they did here is that they'll say, hey, let's actually not do the first differencing. Okay, remember these instruments are motivated by equation 8. Okay, they're gonna say, okay, let's go back to equation 7. Okay, without even take the first difference, because take the first differencing is gonna causing us trouble because we're gonna have the change of capital very close to be zero. what they did is to say, why don't we just instrument for this whole big error term all together, including the omega I. Okay, now you can see this is pretty ad hoc. Okay, so I'm gonna say is that let's look at this big piece of the error term, and then make the assumption that the change of the input is actually uncorrelated with this big error term. Okay, so what they call the level moments equation here is that to kind of provide remedy for this original problem, what they did is try to say any of the inputs and outputs that's t period lagged. Of course, they have to handle these guys, right? They have to make sure it happens before they are realized. That's all okay, right? These are fine. These are fine. If you get anything goes before them, you rely on the same assumption of sequential exogeneity, right? The problematic part is actually this guy, omega I, right? Basic assumption is that, yeah, you can have contemporaneous correlation before the labor and how good an entrepreneur is, but the change of the labor or change of the capital is going to be uncorrelated with this guy. But that's a very strong assumption. But they have to use that anyway, because they have to. If the ideal case is that if you can have your data, if you can use these moments, everything come up like if you have a very large data set, if you have like a few thousand firms use this, things come up reasonable. This is the ideal case, what we want to use, right? But if you suffer from weak instrument problem, the ad hoc remedy they come up with is actually adding this also into your moment condition, okay? And this is what we call the system GMM. They even coded a stata routine for it, right? If you go to stata, type help a bound, okay, that's going to show up. A lot of help files. You can actually implement that. But that's the nutshell of what they were doing. And I just want to ask you to pay attention to this thing, which is there is a strong caveat here, which is the change of input. They are assumed to be uncorrelated with this permanent heterogeneity, okay, which is a very strong assumption. Although if you are thinking about back to a very simple model, it might be okay, because if you think about if the labor, right, is going to be linearly dependent on this AI, right? If you want to call Douglas, if we take an over time difference of this labor, you might actually be able to difference the omega I out. Okay, and in that case, this possibly the one of the few examples that are going to rigorously actually support that moment condition. If you have all the inputs enter just linearly, not log linearly, right? Log linearly in terms of productivity, then it would be fine. Okay, but in any case, this is the first typical method that people have been using, and these are just workout things in the matrices. Don't worry about it. Okay, now I'm gonna go for the second one. Just directly jump into the one that actually relies a little bit more on the model. And after this one, we can have a break, okay? Because this is pretty heavy, so you might need time to kind of digest a little bit. Okay, so this is a paper by Ollie and Pecos in 1996. Okay, so this is very well known and also again very well utilized paper. So here the difference is that this estimation method is actually relies on a very tight model. Okay, they're actually building a very tight model that perfectly rationalizes their estimator. So what the model has shares some common feature with the previous model, but for the most part, it's actually different. And then later, I try to highlight pros and cons for both methods. Okay, so I've been talking about the trade-offs for the previous dynamic panel method. So this one, now you immediately see the difference. Okay, the productivity shock is assumed to be all time varying. There's no permanent observed heterogeneity. Okay, that's very different from the previous one, which we do have a permanent observed heterogeneity case here. Is that clear? Okay. So there are two pieces enter our A shock. One is omega I, now is omega IT, right? The other one is EIT. Again, EIT is the same. It's IID over time. Think about this as the expectational error, transitory shocks, whatever. And on top of that, they're going to try to model the omega as an unrestricted first-order Markov process. Okay. Okay. Again, this is a little bit more general than L1 now. Okay. So what you have is that it's not necessarily need to be linear. You can have the high order terms into entering this whole process, right? That's effectively what they did later too. You know, you can use very flexible functions to think about this first order Markov process. Okay, this is more general. Although, as I said, they lose the permanent heterogeneity, and the timing assumption is very much like what we have been talking about, which is pretty reasonable. The label is flexible input, right? The label will be chosen after you observe the omega it, and the capital is going to be quasi-fixed, so it had at least one period time to build, and likely have some adjustment cost. Okay, so the capital will be slow moving. You know that if you have good productivity shock today, you're going to respond to it, but it won't actually enter into production until the next period. That's their model. Okay, so they in their paper they have a more complicated model, have some kind of game theoretical stuff. I've kind of stripped them out just to give you a cleaner version of what exactly their model will be actually looking like. So what they look like is that. By the way, has anybody seen a value function? Raise your hand if you have seen one. Oh, great. Okay, a lot of you. Okay, so yeah, so the basically what the value function is saying here is that what's the value of this firm, right? When it has this amount of capital stock and this productivity shock. You know, typically the value will come from two parts. One is what current period you'll be getting, right? And then the other one is what we call option value. You know, if you actually decide you want to continue, what are the future value you'll be getting, right? So there'll be two pieces. So here, this will be just the profit. If you decide this is how much labor you want to use, right? So labor is a flexible input. Once you decide on labor, you're gonna get this amount of profit minus any adjustment cost of the capital stock, right? This is I and K. Which this would be like if any investment or adjustment cost will be entering here. And then what you get is the future option value, right? So this is the beta times the expected value of the future. You don't know how good that is, but depending on the current productivity, you will have reasonable expectation about what this future productivity will be looking like. Okay, clear? Is that fine? Okay, this is what you're gonna do. This is what you're gonna have if you decide you want to continue operating. You want to keep going. What happens if you want to just say, okay, I figure I'm just not that good. I would rather just being a university professor. What are you gonna do? You're gonna take the university professor's salary, right? And then you're gonna just quit, right? So you will be. This is a phi. Phi is just the what we call the square value, right? So now you can see a nice feature of this model they've been working on is that they essentially provide a micro foundation for an unbalanced pattern, right? So that's what they did. So they basically saying that under the assumption that I have a square value, we could potentially rationalize the fact that we don't need all the firms to just being kind of continue in this industry. There could be some guy dropping out over the time. It's totally well explained by this model, right? And in fact, once you get the chance to learn more mathematical derivations of these kind of value function, okay? In fact, under their assumption, okay, what will happen is there'll be a threshold for the productivity that out of this problem, right? There'll be a threshold of this productivity in terms of whether you decide to continue or not. That's closely related to the fact that these productivity shocks are actually first order Markov process, right? First order Markov process meaning that condition doesn't matter what happened in the past. I can be getting into the best, like high school, best college, whatever. I don't care. All I care is like how good I am today. Okay. So basically, the firm is going to say, I'm going to look at myself today, right? What my omega it is, and all my future is being just predicted by my current self. The history doesn't really matter. Okay. So under this world, you have a single crossing, which is for the firm with a certain capital size. Okay, you will have a threshold that every firm that had this current productivity above this threshold, they will actually continue, and below that, they will just quit. Okay, so that's the implication of this of this model. Okay, of course, in reality, it's a little bit more complicated because maybe there's not such a realistic crossing. So what you can do is basically you can make the square value to be a little bit random, right? Some guy actually has better outside option, some guy has a little bit less. Then you will be able to generate a probabilistic function, right? That is actually increasing in your current productivity in terms of whether you decide to continue or not. Is that clear? Okay. And you can also see capital play an important role, right? So even I have lower productivity than you guys, but if I have more capital in stock, that makes me also less likely to exit, right? So both capital and so conditional on capital productivity is the only thing that matters. But once we have to take into account the capital too, right? Is that clear? Okay. So that's the implication of this dynamic problem. Okay. Okay. So now let's look at this problem and look at the investment decision. Okay. There's a very important caveat here. Again, is that once I decide that I want to continue, right? Once I decide that my productivity is above this threshold, the second important decision I want to make is that how much I want to invest. Okay, I know that what I invest today is not going to enter my current profit. My profit will be dependent on my previous investment. But what I invest today will be affecting my future capital stock. That will make my future more productive and more profitable, right? So I'm going to make my I decision depend on a few things. But what are the things that these decisions need to depend on? Usually these are policy functions, right? In a dynamic programming problem, this will depend on your current state variables, right? These are the two state variables that you depend on. So your investment decision will depend on your current capital stock and your current productivity. Okay, is that fine? Okay. All right. So the crucial assumption here from this paper, although they didn't, really prove it, they basically claim this as like a very important assumption, is that what we'll have here is that the investment is a strictly monotonic function of omega it conditional on kit. Okay, what does that mean? That means that if the two of us have the same productivity this period, if I see somehow you invest more than I do, then what I can infer, again, if we have the same capital stock today, if I see you somehow invest more than I do, then what can I say? You must be more productive than I am. Okay, basically this assumption makes it possible for people to make this kind of statement, right? They're basically just saying, if I observe your investment, I can somewhat infer how productive you are. And that comes the name to talk about the control function, right? So this is basically just think about using the investment as a control for the unobserved productivity. Okay, is that clear? Everyone, so fine? Okay, all right. So what's going on here is that now you come to this equation 11, which is the productivity will be a function of your capital and investment, right? So this basically comes from this feature that you have this is being a monotonic function in omega it, and this will be this is self-explanatory, right? And this function is invertible because it's monotonic. So the omega it can be written as a function of kit and iit. Okay. Any questions so far? No? Okay. Now you can rewrite this production function as combining this omega it. Again, remember we're still in this Cobb-Douglas world, right? So The production function will be basically combining the beta L LIT, beta K KIT, and this unobserved productivity. Right? Now, but instead of having this unobserved productivity, we have something that's totally known. Right? We just don't know what this function HT looks like, but we know the HT will depend on the investment and the KIT. Right? Okay. So now you can see this method, basically what it does is to utilize more data, fundamentally, right? So compare with these kind of dynamic panel data, which basically saying, okay, I'm just gonna use my input and output, you know, like in the previous period, what this method is saying that, hey, you know, actually we see more data from this firm than just these input and outputs, right? We see something that's actually dynamic. We see some dynamic input, which is investment. And by going from these dynamic inputs, we might be able to actually infer what the unobserved productivity will be actually looking like. Okay, and so this is a pretty neat idea, right? But although, make sure you remember the assumption here, right? This is under the strict monotonicity condition, right? And under the condition that there's only one unobserved productivity term, omega IT, right? Think about if you have two, then you will be pragmatic, right? So, you know, if I see you invest a lot, I never know. Think about you have a productivity term for the production for the goods of the domestic market, and the productivity term for the production of the goods for the foreign market. Okay. Then if I see you invest a lot, I can never infer. You know, is that because you have a good shock in the foreign, or it's have a good shock in the domestic? Cannot separate that, right? So you have to have only one scalar, unobservable, and you have to have this strict monotonicity condition, right? So these are the two very important conditions that we have to rely on. Okay, it is okay. Is this equation okay? Everyone still follow? Yes or no? Okay, good. I see a lot of people nodding. That's good. Okay, so once you go from here, then now let's use the assumption that let's try to beef up this HT. Okay, so the first step is very simple. At least what proposed in the original paper was very simple. What they say is that, okay, you just fill up this unknown stuff with the KIT and the investment data, right? You can do this as flexible as you want, okay? But obviously, by doing that, we won't be able to estimate beta K, because, you know, whatever K ends up here versus K ends up here, we cannot really separate them, right? But, you know, the good thing is we can actually estimate beta L. That's what the original paper was trying to propose, right? Let's do the beta L, and then let's try to do this part on a second stage. The second stage actually applies to like 99% of the following papers. Okay, the follow-up papers. Basically what they do is they have to rely on this Markovian assumption. Okay, what they did is try to say is that the omega IT of this period will be a G function of the previous omega IT minus 1 plus a kind of a random shock psi IT. Okay, so far so good. So basically what they did is that by knowing what this beta L is, we know what this phi, this is phi, right? We know this phi t looks like, but this phi t will be a function of this beta k times KIT plus whatever productivity is, right? So now let's put this estimated phi t on the left-hand side and write out this beta k, right? And then what's inside here is just the g of omega IT minus 1. Does everyone see? This is just the omega IT minus 1. Is that fine? Okay. And then plus this shock. Okay. So basically, this is also called two-step estimation. What they did is they estimate this phi IT in a kind of separate first stage, and then they estimate the rest of parameters from a second stage, which is our equation 14. Okay. In the original paper, what they did is they estimate things like in two separate stages like this. But, you know, there's a paper by Woodridge actually saying that, you know, there's not necessarily you need to do that. You know, you can basically combine these two stages and into a single set of moments of generally maximum moments condition, and then just estimate in one step. This kind of saves you to adjust standard errors across these two steps. Okay, so that's the thing. Okay, all right. So this is a case where we have no. This is a case that we haven't handled this part. Remember, we still have an exit decision here that we haven't really handled, right? So okay, so how do we do that? Now we have to modify this equation a little bit. Okay. Okay, let me just go slowly, okay, because the exit condition is a little bit complicated. So remember, there's endogenous selection. So this is the beauty of this paper, which is it does allow for this endogenous selection directly. If you have endogenous selection, right, what's going on is that the kind of predicted phi t will be rely on this beta k times kit, which is fine, but it also relies on the the expected value of omega it conditional that you are continuing, right? Before we don't have if we don't consider selection, we just directly substitute in the g, then we're done, right? But if you consider selection, you will have to say no, it's not really g, it's actually g but conditioning on something. What does that condition on? That condition on the fact that I have a good productivity draw, right? Condition on my KIT. So this is saying that if I'm continuing, I must be above this threshold. Okay? And the fact that I'm above this threshold means that this threshold should enter into the G2. Right? This is the definition of conditional expectation, right? If we're conditional on anything in terms of expectation, you will enter this function. Is that clear? Good. Okay. So now, essentially, what do we need to supplement with here, right? With here, we only have G. Now we have to actually have a proxy for what this omega bar KIT looks like. Okay. So what do they do? What they did is they put a probability of continuing as a separate estimates to proxy for this omega bar KIT. Okay. So basically what they did, just like in plain words, what they do is they run a probabilistic regression, right, of whether a firm continue or not on its current capital stock and its productivity. And they end up with a prediction of that, right? So basically they're saying the higher, because these things are single threshold, right? So single crossing threshold, they're basically just saying, the higher the probability that is, it must be that this term is actually, the probability must be just only reflecting the change of this threshold terms. Okay, that's where you get these two dots connected. So compare with the standard equation here, number 14. What you have is to embed in this PIT term in here. Okay, this turns out to be a very useful empirical strategy. You don't need to limit yourself to estimating their model. Essentially, any first-order Markov process with a selection problem, right? You could potentially do what we call the correction term using this strategy, right? Okay, is that clear? Okay. Now, okay, they've done a lot of complicated things, but what do people find? In terms of people, at the end, what do people find is in practice, as long as you maintain an unbiased panel, you don't really try to truncate it. You don't really say, I'm only doing a balanced panel. Whether you correct this guy or not actually doesn't really matter too much. That's been kind of shown like again and again after that. So after a lot of complication, you've done that. It's usually like kind of ends up as a robustness check. Right? People do not seem to care too much about whether you've been correcting this or not if you maintain an unbalanced panel. Right? So that's exactly the thing that, remember, for these estimation, you can perfectly estimate that on an unbalanced panel. It's not like in the dynamic panel, you have to kind of go back for like 3 periods to look for instrument, right? Here, you don't need to do that. So estimating from an unbalanced panel is completely okay. Right? What you need is just one lag. So you need 2 periods of data to actually estimate this thing, right? Okay. All right, I'm going to talk one paper very briefly, and then I'm going to move on to a few other more details. So a few years after the Olympics wrote their paper, there's another paper by Levinson and Patron. Basically, what they argue is a very simple observation. related to what we have talked about, right? So think about these guys have been thinking about using the investment as their what we call the control for the productivity. But Levinson and Patron, and by the way, I didn't talk about the application, which we're economists, we should talk about that. The application of this paper is on the U.S. telecom industry. This is about these telecom firms, right? So these are big firms. So what they did is they tried to look at after the deregulation of the industry, what happened to the performance of these telecom firms. And because of these are firms, they do invest quite frequently, right? So that never created a data problem for these guys by seeing the investment data and using their control function methods. A few years later, what happened is that Levinson and Patron, they tried to apply these methods to a few developing countries. They were using Colombian data, they were using Chilean data, Moroccan data. And then what they find is that there's no way to apply this method at all, because for most of these producers, what they have is reporting investment zero. They just constantly saying 0, 0, 0, 0, right? So then what's the question? The question is that we need this control function to work. We need a strict monotonicity, right? If you and I both report 0, how can I infer, whether you are more productive or less productive? I don't know, right? Maybe we all have this kind of hysteresis band of investment. Maybe you're waiting and I'm waiting. There's no way for me to figure out what the omega IT looks like. So they pointed out this problem, and what they did is essentially what they tried to propose is to use an alternative control function. Okay, what they say, okay, what if we don't use investment? Instead, we use the intermediate inputs. Okay, and then by kind of moving towards intermediate inputs, we know that almost every year each firm is going to invest kind of just using the intermediate inputs very, very frequently, right? So they basically overcome this missing data problem, and that's what they did in this paper. Okay, so the whole point is that you don't need to limit yourself to one specific control function, right? Anything that's gonna reasonably satisfy the strict monotonicity condition, you could potentially use that as a control function. Okay. All right. I think let me actually finish this one before we go for the break, because that's gonna give you the whole package. But let me know if it's already too much to absorb. Is that okay? Still so far? Okay, fine. Okay. Let me just do this final one, and then we it's not going to be hard either. Okay. So what's going on for this literature is interesting because people keep proposing something, and then later people keep saying no, there's a problem with it, right? So that's keep coming. So with this paper, Eckerberg et al., what they did is that they effectively come along to say, there's actually a subtle problem in both Early-Pecos and Levinson and Patron that something doesn't work. Okay, what they pointed out originally was the fact that actually, in fact, this claim in the original Early-Pecos paper that the labor coefficient was identified in a separate first stage or even ever identified is not well established. Okay, they're basically saying there's no way you can actually identify the labor coefficient if you truly believe the data generating process is as modeled in the Early-Pecos paper. Okay, so what's the argument here? It's actually a pretty subtle argument that they were trying to make. Remember, in the Early-Pecos paper, right? So the investment will be depend on the capital, and it will depend on the productivity. Is that clear? Okay. Okay. Now let's see what does labor depend on. So labor, right? It's going to be a static choice, so it does depend on capital too, right? It also depends on omega IT, right? And then we know that this is invertible, right? So omega IT can be written as a function of KIT and IIT too, right? Okay. So now by staring at this, now we actually go back to this equation, right? Can you still claim that actually this beta IO is actually identified separately from this function? Not anymore, right? We know that labor will again be just, if you make the phi just completely flexible, if you make this phi completely flexible, beta IO cannot be really separately estimated from a separate first stage, right? In fact, you were running out of data in terms of identify a separate source of variation for labor, because both labor and both the investment depend on the same sets of state variables, right? And you can easily to see Levison pattern doesn't work either, because like whatever intermediate inputs you come up with will possibly suffer from the same problem here, right? Okay, because material will be also a function of this. Okay, so what does this paper do is basically providing a few remedies to say under what set of assumptions that we can still use the early pickers. It's like try to say, okay, maybe people been using are not totally crazy, but let me kind of like try to rationalize that using some more tricky assumptions. Okay, so what did they do? They first show that actually there are two additional variations that might drive labor around, which you could potentially use, but these rely on very strong assumption that we don't really like. Okay, so the first one is that there's a firm-specific wage rate that must be serially uncorrelated. Okay, the reason it can be serially correlated is because if it's serially correlated, again it becomes a state variable. Then you're done. The investment will depend on it, right? So it can be only serially uncorrelated. But again, we know that this is very awkward. We don't want that. We don't really like this kind of wage being exogenously serial correlated kind of idea. The second one is a little bit like in the behavioral sense. It's like, okay, what if like there's a serial uncorrelated like optimization error? I want to choose like 100 workers. Somewhat, I kind of made a mistake or whatever, made some random mistake that I actually picked like 101. But that will actually give you some variation in labor, right? Make it not completely rely on the same state variables. But again, it's not that something make a lot of economic sense. Okay, so these are two remedies. We've seen papers actually making assumptions based on those. But I think what they try to do as the most, almost like the most reasonable, what you can do is to play up with the timing assumption. Okay, what's the timing assumption that they actually play with? I have to say, this is just try to, again, it's not saying that this is the perfect word. There are a lot of caveats there, but this is something, in terms of economic research, my sense is always like, if you don't have enough data, you possibly make more assumptions, right? So that's typically the compromise you will be seeing. So what they did now is try to break the labor with the rest of the economic variables. They try to play with the timing. What they did is just to try to say capital is actually quasi-fixed, still like we used to have. Okay, it's chosen in t period t-1, subject to time to build and adjustment cost. This is the same. This is like early pickers. Okay, material is fully flexible. Okay, it's like you can pick the material once you see everything. You can see material once you see the capital choice, the labor choice, the productivity realization. Okay, but there's a very crucial assumption here. They might say this is entering a Leontief fashion. The material is going to be like having some strict proportionality with like how much output you want to be producing. In fact, it cannot enter freely. There's a later paper showing that if it's not Leontief, then this trick doesn't really work. Okay, so you have to assume a Leontief production function with the material complements with something called value added. Okay, everyone has heard of value added, right? That's just something that capital and labor combined. You have this hypothetical word that once you put them into together, you add on the material. Okay, so the material is in a Leontief fashion. So labor is chosen in a very weird time point, right? Not weird, but in a kind of very specific time point, which is has to be before material, but after capital. Okay, so we call this in the earlier version of the paper they call this time t plus 0.5, right? So that's the middle. Okay, so you can think about the firm. What those are like, okay, I decided how much capital I want to use, right? When I go to the beginning of the next year, I just say, okay, I haven't seen my productivity realized a little bit, but I haven't seen the full realization of my productivity yet. Let me actually decide on how much work I want to have for this whole year. And just put it there, I never change it. And then the productivity fully realized. Okay, I see how good I am. Then I'm choosing my material. Okay, that's the timing assumption being kind of played around by this paper. Okay, so the timing assumption, what is that is, it breaks the collinearity between the labor and the control function material. Okay, so now there's no cross dependence anymore. Okay, basically the material will depend on labor. Labor doesn't depend on material. Okay, so that's the trick that's being played here. And meanwhile, it maintains the correlation between labor and the productivity, because when you choose the labor, your productivity is partially realized. That's why we call that T plus 0.5. It's partially realized but not fully realized. Is that clear? Okay, that's the key assumption here for this paper. Okay, so if you buy this assumption, then what you can do is that you can use this material as a proxy variable, right? And then you can use the lagged input variables as your instrument for the rest of endogenous inputs, which is going to be the labor. Okay, so you can view this ACF as somewhat a middle ground between the original Oedipus, which is purely a control function approach, with some dynamic panel insight, right? Which is, you can now they're gonna turn back to lag labor and the lag capital as instrumenting strategy. Okay, is that clear? Right. So in Oedipus, essentially they didn't use any IV, but here you kind of combining the proxy approach with the dynamic panel literature a little bit. Okay. So here's the detailed procedure. I'm going to go, given what we explained, it's going to go very quickly. Okay, it's basically you have a value-added production function. Okay, this is a value-added production function. Remember the Leontief. Okay, that's the Leontief word. Material doesn't enter the value-added production function. It's only the capital and labor. But the material enters as a proxy. Proxy for what? Proxy for the fully realized productivity. Okay? So now you have a first stage which looks like this. But then you have your output depend on these three things together. There's no hope you're going to separate out any of the production technology in that stage, other than you're going to tease out just this transitory shock EIT. Okay? So nowadays, when people estimate these production functions, they will usually call the first stage to say filtering stage. Okay, what are they filtering out? They're actually filtering out these transitory shocks. Okay, once they filter out these transitory shocks, they were actually looking at a second stage, which is looking at this phi function minus the alpha k kit and alpha l lit. Okay, which is essentially saying that they're identifying the capital and labor coefficient simultaneously in the second stage, okay? And using one moment conditions, very similar to dynamic panel. They were using the KIT to instrument for, they don't need to use KIT. This is just like, KIT is going to be a dynamic input, so KIT do not suffer from endogeneity problem because it'll be, by definition, uncorrelated with CASI-IT. Only the future KIT will be correlated with CASI-IT, right? Labor will be, but you will be using the lagged labor as your instrument. So you'll be using these sequential exogeneity moments to estimate this model. Okay, so it's a hybrid, right? Now you can see it's a hybrid. To a certain extent, equation 19 is borrowing a lot from the control function, like Audi and Pecos and Emerson Patron, right? 920 is very much like a dynamic panel. We're using these lag moments, sequential exogeneity, to actually estimate the model. Okay, is that clear? So that's I would say, like, if you go back, if you look at the previous 5-6 years, most of the paper have been using this kind of setup to estimate the production function. Okay, so there's something I want you to pay attention to here. Okay, if you happen to study the producers that face output or input market distortions, okay, think about firms in China, or you think about any firms in other developing countries, okay, or any firm that's actually in an imperfect competitive market. What you need to pay attention to. Okay, so the examples will be, the firm have pricing power, right? The firms actually facing credit constraint, or maybe you have firms that actually facing some labor surge frictions, the labor market frictions. You need to check very carefully whether this monotheistic condition actually hold for your proxy method or not. Okay, this is something that actually non-trivial. Remember in the Oedipus example, I was showing a very simple dynamic programming problem, but once you start to have these setups, it's not clear whether the investment will be monotonically increasing in productivity or not. You really want to carefully check that. You want to make sure that partially that's a problem with the Oedipus method is that it's coming from a very tightly modeled data generating process. Okay, it's not a method that's kind of like you really need to check a lot of the conditions for that to be applicable to your own data generating process, right? So this is the first thing you may want to check. The second thing, as I already mentioned, you might also want to think about whether this actually need to control for additional unobservables, right? If you have additional unobservables, very likely you will need to have additional controls, right? One control variable might not be enough. You might actually need to come up with two control variables, right? That's the other thing that you might want to pay attention to. Okay, so just to summarize for this literature, dynamic panel allow for permanent unobserved heterogeneity, which is attractive. AR1 a little bit more restrictive, less flexible than first order macro process. Remind you, sample selection problem. Okay, and the level equation not very co-founded. Level equation are the ones that are actually instrumenting for the omega I, right? They're not micro-founded. Proxy method, which is a control function method, no time environment observable, right? That's a downside. But the nice part is elegant solution for the selection, right? Okay, have to pay attention to the monotheistic and scalar observable conditions depending on the detailed data generating process. Okay, so this is my kind of like summary slides in terms of a quick lecture about what these two things look like and what kind of trade-offs you will see coming from these methods. Okay, all right, great timing. 3:30. Let's have a break. Okay, so here. Okay, so here for this first part, I basically tell you about the basic methods and also the what are the typical econometric concerns. And now, if you are an empirical researcher, you will start to think about there are a lot of practical issues that you will face too. It's not only about like econometric issues, but also practical issues. A very well-known. So now for the second part, I'm going to talk about a few practical issues, and just to the most important one that has been very well known here is the what we call omitted price bias. Okay, so the omitted price bias is just being raised in this early paper again, very underappreciated paper by Klater and Gridikis. What they basically think about is that what is basically pointed out is that so far all the models we have been working on in terms of production function, in fact using physical quantity and output and inputs. Okay, but commonly observing the data is really not that. What we see is the revenue, right, and we see the input expenditures, right? Okay, so it's fundamentally a very tough data issue, in terms of basically what they point out is a kind of like how to separate P from YIT and how to separate PITX from XIT, right? So this is the what we call omitted price bias. There's some progress on this literature, but I want to show you basically two papers just illustrate what are the typical way that people have been using to overcome this kind of problem. To summarize them, actually, is going to be surprisingly simple. Okay, the first one is to collect more data. Okay, so that's almost like self-evident. You want to collect better data. If you do see the price, you do see the input price, then you possibly will be fine. But if not feasible, then we will have to make certain assumptions. Okay, And a lot of cases that people making assumption will be on the demand side, okay? And the most commonly assumed is the monopolistic competitive model we see as demand structure. That's what typically being assumed to overcome this non-observed output price issue, okay? The input price is even tougher. I possibly won't have time to talk about it, but the almost input price will be another major problem here, okay? But sometimes, again, what people have been doing is to kind of just assume away the problem for material and then consider estimating a value-added production function. And then another strategy to think about is that maybe there is some relationship between the input and output prices themselves. Okay? That's another way that people have been using to kind of address the unobserved input price problems. What they did is that try to say, okay, despite I don't see the input price, the fact that I see the output price, conditional everything else, if you are a firm that produce higher output price product due to you're actually producing high quality, you must be using high quality inputs. So let me use that to proxy for that. There were recent papers that have been using this type of strategy. Okay, so these are the three commonly used strategies, and due to the time limit, I'm going to go more briefly on an example paper for each of these things. Okay, to just tell you the first paper that actually try to collect better data to actually think about this problem, that will be the paper by Foster, Hortweiger, and Syverson. Okay, so what they did here is, again, as we've been emphasizing, because we don't see the price and the output separately, there's also a tougher time that we can separate effectively what's demand and what's productivity. Okay, so if you see a firm, basically the point is that if you see a firm which generates a lot of revenue, okay, so there are three explanations for that, right? One potential explanation is that there are some idiosyncratic demand shocks. Okay, the firms just being having a lot of customers. The second explanation is that the firm's having a lot of production efficiency, right? That's a very productive firm. And third one is that maybe they have some market power, right? So how do we actually tell that apart? And at the end of the day, I don't think they really tackle this problem. I don't think they really tackle market power. But in general, what they try to say is that if we see the quantity and price of the output separately, then what we can do is to use the quantity and price data to figure out how high the demand shifter looks like. Okay, by literally estimating a demand function, demand curve, right? And then from the production side, we can separate out what the production efficiency looks like. So by having the quantity and price separately, not only allow you to measure the production efficiency more precisely, it also allows you to use the quantity data to estimate the demand function such that you can trace out the demand shifters, right? So that's the basic idea of this paper, okay? But their arguments not necessarily apply to each industry. What's the reason for that? There might be some industry which products are very differentiated, right? So you can think about there are industries that there's products are so different. How do we compare a car of Maserati, right, versus a car of Honda, right? The quantity is just not fundamentally comparable. There's no reason we should think about a firm that produces 3 Maserati actually less productive than a firm producing 10 Honda, right? So this is just completely different segment of these products. So basically, what it did is actually not only to collect more data, that also limit them to a much narrow set of industries that can be applied this idea to, right? So what they did is they focused pretty much on physically homogeneous products, and also on these products avoid large quality variations. These products all look very much the same across different producers. So what are these products that they use, right? But they use ready-mix concrete. A lot of the friends of a lot of IO economists, right? So the raw cane sugar, white pane bread, ice cubes, right? A lot of these things, which you can imagine, there's not much quality differentiation that you can think about for these firms. And then what they did is to basically separate out what they call the physical productivity, which is based on quantity, and what they call the revenue productivity, which is based on price times quantity, and effectively that's the price times the physical efficiency. Okay, I'm not going to go too much detail into this demand structure they actually put up there, but again, just by looking at this formula, what you can see is that the key point is that if you don't separate physical productivity from revenue productivity, and if you use revenue data, what the revenue data is going to give you will be effectively a combination of the physical productivity and also the demand shock, which is the delta I. Okay, so the two measures are actually positively correlated, but TFPI is actually confounded by these demand shocks, and they also have some kind of like factor prices in there. Okay, so that's what they try to argue for. Okay, and because they have these ideal data, they can separate price and quantity. What they did is essentially try to separately measure the TFPQ and the TFPR, right? So the TFPQ will be coming from that they use the physical quantity data. So the YIT is going to be the quantity, the physical units of the shipment for each of these census of manufacturer producer goes from 1977 to 1997. So they were basically using the physical quantity to estimate the physical TFP, and then they will be using this physical TFP also to compare that with the revenue TFP, and they will be using this for also one more. So what do they find? What they find is that the TFPQ, what is out of here, is typically more dispersed than the TFPR. Okay, so what does that imply? That implies that there's actually negative correlation between the price and the physical productivity in their data. Okay, so because you are more productive, you're also inducing lower prices, right? Then that's the more productive guy will having charging lower prices. Then overall you see a more condensed the distribution for TFPR for revenue TFP compared with the physical TFP. Okay, that's the first finding. Okay, and the second finding that they have is by actually estimating this demand equation. Okay, so because they observe the price and the quantity separately, they could estimate an equation of log quantity on log price. Okay, and by controlling for each market's income. Okay, all right. So if we want to estimate the demand equation, what's the basic challenge? That's because the price is endogenous, right? So you need to find an instrument for the price. What kind of instrument you can get for the price? If you want to estimate demand equation, you need what kind of shifters? You need a cost shifters, right? So the cost shifter, what they happen to have here is what they have is this physical TFP. Okay? Because in this stage, they've recovered the physical TFP, what they're going to do is to use the physical TFP as an instrument here for this price to estimate their demand curve. And what does demand curve give them? It gives them the demand shifters, right? What they call the demand shock. Okay? Once you get the demand shock, you can basically compare basically the fundamental question of this paper is that we see revenue TFP to be very important in determining firms' survival, right? In determining firms' growth. The question is, within this revenue TFP, really is it productivity or is demand shock? That's the question. Okay. So what did they find? What they find is that the entrants of each industry actually have significantly higher physical TFP compared with the incumbents. Okay. So the new entrants actually turns out to be better in terms of physical efficiency. But why they are smaller and why they cannot survive long enough? The problem is that this advantage is clouded in the revenue productivity because they have much lower demand shocks. Okay, this term is actually lower, that means that even they charge the same price as the incumbents, they will sell much less than the incumbents. Okay, so this makes a lot of sense, right? Think of any new firm you break into a market, you don't have existing customer base. You really have to accumulate the new customers. So that's basically talking about, the advantage of the profitability of the firm actually coming from both efficiency and demand side. And for the new entrants, actually demand is a key determinant of its survival, right? So in terms of selection, what they find is that the demand is a lot more important than the physical productivity. Okay, so the fact that you can think about in China, the fact that Alibaba is successful, or any kind of the local producer is successful, most likely is because they have this bigger customer base, instead of the fact that they're actually the most cost-effective firm in the market. Okay, so this turns out to be 3 times more important than the physical productivity in determining the survival of the firm. Okay, so that's what they're finding. So this is actually economically an interesting finding, but just to highlight, it's not possible to separate these two unless you have the quantity and the price data separately, right? So this paper basically what they did is to collect. This is first approach, right? Basically just collect better data. So you do have the omitted price problem, but you collect better data about price, and you have the quantity, and you can do a lot more effectively. Okay. All right. So now I'm going to tell you the second piece, right? So most of you possibly want to use Chinese data. You're going to use Chinese manufacturing survey data. Hopeless. There's no price, right? What can you do? If you cannot get more data, you make more assumptions. And the typical assumption that's been very convenient is kind of this assumption, right? This is the paper by Ian DeLocker, right? In Econometric. Okay, so what's going to happen here is that for most of the countries, for these manufacturing survey data, we don't really see price. If you don't have a perfect data like Forster, Hutchinson, Stevenson has, what you want to do is to actually think about making some progress based on more assumptions. Okay, so in fact, their assumption is very close to the original strategy by Crater and Grikis, right? So what they did is to restrict the demand to be having constant elasticity. Okay, and the additional data, and you also need some additional data that might independently shift the demand. And in this paper, that's one contribution of this paper is actually using some observable demand shifters, right? So he was looking at this paper was looking at the Belgium data, and what paper relies on is to think about that there are these quota restrictions for the EU market, restricting the competition coming from outsiders. Okay, and depend on each product subject to the different quota, right? So the market condition, the effective demand, the market size facing these producers' products actually vary, right? And there's also rich over time as well as cross-product variation in these quota restrictions. Okay, so basically the paper combines the assumption of the CES demand together with these observable demand shifters, okay, to actually estimate a model with the OP style proxy methods. Okay, is that clear? Okay. Okay, I'm going to show you a little bit more details before we go on. So interestingly, he wrote the paper before the this paper. Yeah, that's what I'm saying. That he wrote the paper before ACF was again criticized. So he was using ACF, but in a little bit wrong way. Later, people realized that actually ACF can only be applied when the production function is Leontief. But nevertheless, this paper got published by having Cobb-Douglas. But that's the progress, right? So we now know Cobb-Douglas doesn't really work. But this paper has a Cobb-Douglas production function with the material inputs here, right? So labor, material, and capital all actually enter here. If you write a paper yourself, you better make sure it's actually Leontief. Okay? So the demand actually depend on some kind of segment quantity, right? So this is This is going to be a specific product segment. Think about this as some kind of specific textile garment, in Belgium. And your price, which is PIT, and the segment price index, PST. Okay. Trade people love this model, right? And IO people hate this model, right? So depending on who you're selling a paper to, but without price data, that's the best you can do, and what you have is the PIT over PST and subject to a constant elasticity eta S, right? This is what we call the CES demand structure. So why actually IO people hates it? It's constant markup, right? So all the firms are gonna charge the same markup, right? And then which typically is not gonna be true for an oligopolistic setup, but if you have a lot of firms, maybe that's a good approximation. So anyway, so that's the assumption that's being imposed here, and then what you have is another demand shock Kasai IT. This is the demand shock. Okay, so given what you have seen, I'm going to just rewrite the revenue function in terms of quantity, and everything's done. The rest you can just apply ACF. There's nothing new there. Okay, so I'm going to just show you one equation, and the rest will be pretty much the same as just ACF that we have gone over. Okay, so what does this revenue? This is the revenue that using your realized revenue data minus the sectoral price index, right? This is the PST. This is going to be the sectoral price index. Okay, now we know that this revenue will be again a function of labor, material, capital, and the sectoral quantity index, but every one of these coefficients actually means something very different compared with the technology coefficient. Okay, here what we do is a very simple step. Basically what we did is to make sure that we'll be writing the revenue, right, equal to the price. That's the big R, like price times the quantity, right? And then from that equation, we know what? We know that the price equal to the quantity of your own divided by the segment quantity index, right? 1 over eta S times the exponential of the Kasai IT to the power of negative 1 over eta S, right? And then you're gonna have this times PST, right? Okay. So this is your price. This is the price, and basically we're gonna just write the revenue as your own quantity 1 plus eta S plus 1, right? So this will be the transformation that I just substitute this in, and plus times the rest of the terms, okay, including the demand shock. Is that clear? Okay. So now, given this QRS, I have to reinterpret, right? The log revenue will be equal to 1 plus 1 over eta S times the log QIT plus log all of the rest, right? Okay. So what we effectively been estimating are these betas, but these betas are actually 1 plus 1 over eta S times the original coefficient. Is that clear? Everyone see what I'm saying? Right? So the betas will be just transform the coefficient. This will be just if we think about this as inverse markup, because in the constant markup world, that's going to imply to be a markup. It's beta basically is the inverse markup times the coefficient in the original production function. That's how the transformation being made. Okay? That's why CES is nice. Why it's nice? Because actually you're going to write the the revenue will be just a linear transformation from the quantity, so that despite that you don't see the quantity at all, the revenue can infer what the quantity looks like. That's exactly the beauty of the CS, right? So that's why when you impose this, actually observing revenue, the output omitted price problem actually just basically resolved by assumption. Okay, not necessarily that's the most reasonable assumption, but still that's a way to make some progress, right, in here. And then the rest will be just handled the same. Okay, so once you go to this equation, right, you know how to estimate it already. That's just the ACF, right? This is just the starting point for actually applying the ACF equation. Okay, with some twist. Okay, so this paper actually made two subtle points, which I think are pretty nice. So I want to highlight a little bit. One subtle point is that these demand shocks partially is observable, right? That's what I'm saying. So it's using the quota restrictions in Belgium textile market. So the demand shock basically is using the quota, the kind of a product, right? That's each product has its own quota, right? And the segment, and then you can create this QRIT. So you can include them directly in your revenue equation, right? So this is what we call observable demand shocks. Okay. You wonder why it's I. That's a very popular empirical strategy these days, which despite the fact that most of these variations is actually at the firm level, because firm is producing multiple products, you can use these weighting to create actually firm time specific protection component, right? That's something that you can put into your revenue equation. That's the first. That's the first first piece of additional data. I think is pretty nice. The second piece of detail is that nothing will restrict. You have to have an exogenous productivity process, right? So you could potentially also have an augmented productive process, which makes whatever happening in some institutional details also affect your productivity evolution. So this is what he put there. Basically what he did, he put also the quota restrictions into the productivity process to argue for some X efficiency story. Okay, so that's the other modification that he did based on the ACF. But despite everything, just the rest will be just ACF. Okay, so that's basically what he did. Okay, so that's, as you can see, once we are done with the previous framework, covering a paper in Econometric is not going to take us much time, right? So that's the three major things that you should pay attention to, and then that's the paper. Okay, all right. So now, what does he? I'm going to briefly go over just in terms of what he got, and then I'll just talk about something new. This is what he talked about to be the augmented production function. Okay, by augmented meaning that he's going to estimate the beta. Beta is going to be the transformed coefficient. This will be the alpha times the inverse markup, and these will be the alpha, which will be the true coefficient. Okay, so what do you find? What you find is that actually once you transform the beta into alpha, it starts to imply the technology has a very strong increase in returns. Okay, so you can see when you add these coefficients up, this will be like I don't know, 1.4. It's super high. I don't know how reasonable that is, but that's the implication of applying that. That's the feature. That's a feature and also a risk. Once you're using this revenue production function and you literally interpret that as an augmented coefficient, then how much the markup is going to make a big difference, right? Here, what he estimated is that it's a not very elastic demand curve, implying that the inverse markup must be very small. The markup will be high, the inverse markup will be small, right? So that implies that if you interpret the revenue production to the physical production, you have to inflate these coefficients quite a lot. And that gives you a very strong increase in return here, okay? I don't know, the paper got published, so I don't know whether this is reasonable or not, but in general, I think this will create trouble if you want to feed that, again, into a bigger model. If you want to feed that in a bigger model, increasing production function at the micro level, increasing return production function at the micro level will usually create some trouble, right? So, one implication is that the industry will kind of getting more and more concentrated over time. The question, do you actually observe that feature or not, right? So this is something you might want to be paying a little bit of attention if you want to apply these kind of methods, okay? At least make sure the demand is not too inelastic. Then you don't need to make too much difference between these two, okay? All right, so that's the two examples. Let me just talk a few recent progress. I think I'm kind of quickly running out of time, but I don't want to spend too much time on the production function, and I will leave some time for something else. There is this very nice paper by Gandhi et al. Around 2016. I think what they basically, their intuition is that, again, as I already said, first of all, they show that actually the ACF doesn't work unless the material inputs is actually Leontief. Okay, that's basically restrict the application of that. And then what they show also is that even if it's not Leontief, what they can do is to supplement the existing techniques with these first order conditions of the variable inputs. For instance, if you have material, right, and if something that's totally variable, you might want to impose additional theoretical restrictions on this estimation procedure, such that you can actually overcome that identification problem that they challenge the ACF. Right? So these guys basically propose to supplement the original methods using these additional first order conditions, which is pretty reasonable. I mean, given the fact that a lot of older literature, when I talk about those literature in the 60s and 70s, in fact, that's the literature actually use a lot of these first order conditions. They use that too much to a certain extent, right? So they use that for each inputs. Right now, with basically the idea is you used to use that for the only one truly variable input here, right? So that's, again, knowledge rediscovered after like 30, 40 years. So the second direction people have been looking at, related to this transstock production function, and try to think about cost minimization and back up some markups. Okay, some Deloka Wasinski and some recent paper by his work with Penny Goldberg. These are all forced into this class. Again, here the key thing is that you have to be very careful about the distinction between physical productivity and the revenue productivity, as well as the output price and input prices. And if you read that paper, you'll see how important these things are. These are more still close to the methodological progress. The later two will be more like, these two will be more like, even from a modeling perspective, there'll be some changes there. Okay, the first one will be by the Dorosowski and Germanju. Basically, as I keep emphasizing, so far we've been seeing all the factor neutral production function. Okay, and they start to think more carefully about if you have a factor augmenting technical change, what the production function estimation problem should be looking like. Okay, and the final paper is by this paper by Halpern et al. in AER. What they did is they dig a little bit deeper into the material inputs, right? So basically, firms can purchase a lot of different intermediate inputs, and the question is, whether some of the intermediate inputs turns out to be more higher quality or like more important than the other ones. So basically, what they did is like kind of try to model both the domestic and the imported intermediate inputs, and then embedded this input choice problem, within the Olipakis ACF framework. Okay, so that's another specific application you can think about, which might be useful extension for these kind of methods. Okay, so these are basically the much more recent paper. You can see the years. Okay, it's like either 2015, 2016. These are where this whole literature has been moving towards. Okay. All right. Okay. Any questions about about things here? Okay. No, if no questions, I think we have around like 40 minutes. I'm gonna go very quickly on the second topic, which is the endogenous efficiency. Okay, so again, we're actually spending very limited time on two very broad topics. So I have to be very restrictive. So now I'm going to restrict our attention to a few papers that actually have quite detailed industry background. They have micro data, which construct the models of firm optimization behavior of learning and innovating, and also talk about essential elements of technology. We'll be very clear about what these technologies are. Okay, so again, before we go into the details, just like the production function estimation, it might be just useful to also step back to think about why these are actually interesting and important things that you want to investigate, right? So there are a lot of very broad kind of motivations, right? You can think about from the kind of the most ambitious, the kind of biggest type of motivation, thinking about how things being driving the endogenous growth. This kind of endogenous growth models, right? You think about Romer, Grossman, Helpman, Aguillon, and Howitz. These are the models that actually rely heavily on us to understand, this innovation and the technological choice problem at the individual firm level, right? So, and also it's a good question about whether the innovation is coming from the entrants or coming from the incumbents. Then, you have these industry dynamic models, like Jovanovic, like Ericson and Pecos, which again, a lot of these elements depend on learning. Okay, a lot of the elements depend on active investment. And also, these things are very much closely related to any of the industry and tax policy. Okay, so if you want to look at how these policies are affecting the firms, you cannot say that without actually thinking about firms being endogenously responding to these things. Okay, so I'm going to briefly talk about a few papers in terms of the endogenous technical change. I'm going to focus on two types of models. Okay, one type of model is what we call passive learning. Okay, basically these are what we call learning by doing models. Okay, learning by doing will be so I'm going to focus on two papers. Both are relatively straightforward, so it's going to not take us too much time. The first paper by Lanier Bankard and the second one by Kellogg in 2011. We can see the learning going on can be both depend on each individual firm's own experience, could also based on the experience it has with its business partner. Okay, so that's the overall, that's the passive learning stuff we have been thinking about. There's even bigger literature which is about the R&D and innovation, which we typically call active learning. Okay, that will be including again, Gradikis has a great book, right? And he's been talking about knowledge capital model, and I'm going to think about an augmented model that I wrote for AR in terms of thinking about this problem. Okay, then I'm still going to think about how firms being indulged in making their R&D decisions. Okay, so that's kind of the roadmap in terms of what I'm going to talk about for the second part. So I'm going to very quick for the first part. What is learning by doing? Okay, the learning by doing actually is very interesting phenomenon. Effectively you can see there are really a lot of micro implications. First of all, let's just try to define what learning by doing is, right? So basically, what learning by doing is going to depend on this key concept that output decision is actually dynamic. Okay, so usually when you make the output decision, you will make sure that your static marginal cost equal to your static marginal revenue. Right? Okay, so now with learning by doing, what's going on is that you effectively also have to factor in the discounted future value, discounted present value of the future cost savings, right? See, what kind of industry you will expect to see these kind of things happening very rapidly? One example is these kind of like semiconductor foundries, right? So, if you think about this is the first batch of the semiconductor component you've been producing. Typically, it's pretty costly, and once you're getting better and better at it, the cost curve, the cost will actually moving quickly down with the cumulative output that you have, right? So these are the typical definition of learning by doing. It's very interesting because, first of all, it feeds into a lot of the macro models, right? But it's also interesting on itself because it has very interesting welfare consequences on a few subtle issues. Okay, so the first question is that with learning by doing, actually, it brings quite interesting trade-offs in terms of the what do you think about the firm's market power? Okay, why? Because the market power is already going to be. We know that market power will be a problem for consumer welfare, right? And here, the market power is actually going to be a problem not only for consumer welfare but also for firms' production problem, right? So the question is, if you were a social planner, you would potentially want the firms to actually moving down its cost curve quicker than what the firm's been doing right now, right? So the private optimization problem typically under the firms having imperfectly competitive market will be different from the social optimal. That makes this phenomenon even more interesting than the standard single agent problem, right? Okay, and the other thing is that in these cases, some IO questions becomes even more interesting too. Because if you think about entry deterrence, right? What's going on is that if you have an industry with quick learning by doing, then the fact that the incumbent can quickly move down its cost curve, there's a lot of incentive for them to speed up, to kind of deter the entry of further competition, right? So there's a paper by Cabral and Royden which actually talk about these facts. Okay, so theoretically we see a lot of interesting implications. Empirically, it's very hard. Okay, there's a kind of relatively weak empirical case studies for these kind of phenomenon, especially in the modern standard kind of econometrics. Okay, so basically I'm going to show you two examples. Two examples pretty much, will be just take one graph. Each of them will take one graph. You will basically see what's going on. Okay, so that's the idea of these papers. The first paper is by Bankard. So in this Bankard paper, he's going to argue that not only learning by doing is actually very important, but also there's non-trivial forgetting. Okay, in some sense that the firm's production experience does accumulate over time, and it's actually going to move down your unit cost. But meanwhile, there's also non-trivial forgetting, organizational forgetting, what they call, by non-trivial like worker turnover, by the fact that this production knowledge just got forgotten once your output actually goes down. Okay, so he'll be looking at the commercial aircraft industry. So this is an industry which is first of all, we know that that's important, right? So there are not that many aircraft manufacturers. What you also have this massive entry cost, right? It's imperfectly competitive, and it has a lot of industry policy across the countries. EU tend to support Airbus. US will support Boeing. There are a lot of policies targeted. China started to support its own aircraft manufacturer. So basically, what he did is to get a very unique data set from one of the major aircraft manufacturers and have their very detailed production data and cost data. Okay? How he managed to do that? Because that company went bankruptcy. Okay? So keep your eye open for any bankruptcy firms. You might get very unique data. So that company went bankruptcy, and he got all the production data, and that's what he had. I'm just showing you a graph. Okay, that's basically his data. Okay, so basically what his data is having is that these are the number of units. Okay, so sorry. This is a timeline, and this is the units per year that this company has been kind of producing. Okay, and these curves are actually the 1,000 man-hour per unit that go into these units. These are the same aircraft. There's nothing changed. It's all the same wide-body engine aircraft. Okay, as you can see, there is a dramatic decline in terms of 1,000 man-hour per unit, right, from the very beginning, right? It tends to, it's like goes from like 1,100 hours all the way down to around like 200 hours, which is a dramatic decline, but also it bounced back a little bit, right? So that this graph basically kind of tend to already show you that these kind of over time variation is going to indicate that the separate important role for learning by doing and organizational forgetting, right? Without organizational forgetting, you should never expect these things to go back, right? And then combined with the units per year, you start to see that when the units goes up, cost actually goes down quickly. But then at one point there was some kind of crisis that the units actually went down, right? And then the cost curve just basically bounced back, right? So the over time pattern actually shows a pretty interesting motivation for this kind of learning by doing model that he will be doing. Okay, is that clear? Okay. So here's what the production model will be looking like. Again, we have our old friend Leontief. Okay, so what he did is that just saying, I have a fixed capital. Okay, so all he's going to focus on will be unit cost of unit labor. How many man hours per unit? Okay, what's the argument for that? That's related to some industry details. Okay, so what's going on here is that you will be having a Leontief function in material and labor. Okay, so this first part will be just this first part will be just labor, and the second part will be just material. Okay, why they're separable? He basically makes an argument that most of the material will be just engine. Okay, engine is the greatest input, but the engines are typically subcontracted. Okay, so and also of course one airplane, one aircraft, two engine, right? One aircraft, two engine. So there's fixed proportion, right? So it doesn't go that bad, right? So that's what he's been arguing. That basically limits his only attention to Q equal to this G. Okay, that's the output, and this is the labor input. Okay, then he makes sure that the labor input essentially enters as like a Cobb-Douglas production function. So what does that imply? If you have a production function which is Cobb-Douglas, by cost minimization, what should be the labor demand function looks like? Labor demand function will also be Cobb-Douglas, right? Okay, so that's why the labor demand function inherited the Cobb-Douglas production function. Okay, and it depends on three things. It actually depends on the fixed capital you have. It depends on the experience. The E is very important. E is learning by doing. Okay, so the E will be the experience, and S will be just some kind of line speed that he can pretty much observe from his data. He's gonna later worry about the endogeneity of these things and provide some instrument, but given this is a single firm, right? All he needs is just over time variation in the instrument, so that'll be easy to find. Okay, so how does he model this learning? EI. EI is the rate of theta is the rate of learning, right? So how does he model this EI? He's gonna think about this company only produced two types of aircrafts. Okay, so one type is what he called Model 500. The other one is called Model 1. Okay, so basically what he did is to have this specification. Okay, so the experience of Model 1 will be coming from a depreciation of the previous experience, right? Plus the current output plus the current output, right? Plus the output of the other model, but subject to some spillover parameter. In principle, this will be smaller than 1, right? The other model won't be as effective as your own model in improving your experience. That's okay? Okay. All right. So the other one will be just the same. It will be symmetric. So what are the parameters of interest? It will be both this lambda, right? The lambda will be this crust model spillover, and the delta will be the depreciation, will be the organizational forgetting. Okay, and the theta will be learning by doing. So remember, we have 3 parameters you might be interested in: theta, lambda, and delta. Right? These are the things that we want to estimate. Okay, and the rest is very simple. Okay, you just need to find some instrument for these 2 variables, SI and EI. But again, as I said, this is only for a single firm, so you only need over time variation in the instrument. And turns out, okay, but let me go back again. Basic question. This is an input-demand equation, right? If we want to instrument these things, what kind of instrument do you want to think about? Is EI and SI? This epsilon I is supposed to be some kind of productivity shocks, right? Okay. What are the instruments you want to? Let me just say this way: if you want to estimate a cost function, what kind of what kind of instrument you want to use? Remember, it's always the opposite, right? If you want to estimate demand, you will use cost shifter. If you want to estimate a input demand, like which is coming from a cost minimization, you will use demand shifter. Okay, that's basically the idea. Okay, so effectively what you do is you're gonna do the demand shifters, right? So these are the 2 demand shifters that's going to move things around. You know, he's going to say world GDP measures. That's the nice part of using aircraft, right? So other things, you know, using world GDP measure possibly, you know, that's going to be problematic. But maybe this is not too much. Price of oil, right? These are the demand shifters. And then he's also going to use some cost shifter here, which you know, because this is a single firm, he'll be using some input aluminum prices and the U.S. wages, and estimate these models using GMM. Okay, turns out OLS and GMM do not actually make much difference. So what he found, as I said, with this graph, what he found is that you know, there's a very strong learning by doing. Right, the theta is actually negative 0.65, and also there's organizational forgetting. Right, so this delta, you have like 4% of the knowledge depreciated every year, and pretty strong cross spillover. You know, different model. You know, your own model actually enters with 1, the other model actually enters with 0.7 of that quantity. So you do have pretty strong cross spillover here in terms of these these learning. Okay, so this is one of the few pieces of interesting empirical pieces for thinking about the learning by doing. Okay, so if you only have learning, you don't have forgetting, you will tend to see a curve looks like this. Okay, but if you look at the full model, what he shows is that you can actually fit the curve really well. So this is basically the fitted curve, and this is the actual data. So his model actually fit the overtime changes of these 1,000 man-hour per unit very, very well. Okay. All right. So this is a simple paper, right? Very, very easy. Okay. I think I'm going to move on and just I'm just going to be very quickly talking about the catalog paper. I'm not going to go into details. So the difference from this paper, I mean, to a certain extent, is really just about dig deeper into the learning. Okay, if you think about some firms being doing better, what do they do? So here there's what they did is that it's actually showing the empirical setup is that he's going to go to the oil drilling industry. Okay, so in front of the oil drilling, what you have is that you have both the company who's going to be contracting and knowing what the geography looks like, and these are what we call the producer. So these are the producer that's who's going to decide on how to look for the right well to actually drill. But for this industry, interestingly, most of the equipment, especially the equipment to drill at the rig level, is actually subcontracted. So have to contract with these company to actually. So the producer and the rigs have to contract with each other to decide on how to drill a well. Okay. So basically, what he did is to try to separate to say, once we see a firm start to drill a well, okay, do we observe any learning outside of the firm? Okay, so is that a fact that actually the firm itself been learning, okay, or it's because the firm's been coordinating with its business partner, which is a rig, and there's kind of like a relationship-specific learning. Okay, that's the paper's point. Okay, so I'm not going to go detail into this paper, and if you're interested, you can basically look at paper itself. It's also straightforward enough. Let me actually move on to the wow, this is too. Let me move on to the let me try to move on to the R&D decision, but before I go there, I want to make sure if you guys have seen this. How many of you have actually learned dynamic discrete choice model? Quite a lot. Maybe I should just go. Okay, let me actually skip this then. Let me just go directly to the model. Okay, so for those of you who haven't actually done that, I actually provide a few useful slides. You know, I'll just distribute the slides. You can from these slides you can think about the dynamic discrete choice model. Okay, so so here what I'm going to do is to apply these dynamic discrete choice model techniques to R&D decision. Okay, so what we're doing here is to try to think about we have panel data, typically has very detailed information about firm sales, right? Their inputs, and what if you have a data with both of these and also other activities, you know, including the firm's exporting and including their R&D. Okay, so these are the data that's very standard you can use for production function estimation. Is that right? Okay, that's the whatever Audipakers, you know, ACF. That's what you can do. And now we're gonna combine these data with these dynamic discrete choices. Okay, so you can think about R&D, whether you do R&D or not, right? That's a discrete choice, and also whether you export or not. That's also again a discrete choice. Okay, we're gonna combine the production decision with dynamic decisions. Okay, so again, there will be strengths and weaknesses of this kind of approach. What you have here is that these will be ideal if you look at individual firm behaviors, right? In production-related activities, these data will be ideal, but very limited information on demand, as I already said. Typically, have to make strong assumptions. That's what it will be doing. Okay, so basically, you can think about in big picture kind of view. But I'm going to combine the production function estimation approach I told you about with Clatan-Gridicus and DeLocus insight that you're putting a CS per demand structure and putting the dynamic discrete choice. Okay, so there's three pieces of these things together in understanding the dynamic decisions in terms of, you know, that's what you need, right? So if you want to model how a firm make their dynamic decisions, these are the three basic fundamental pieces you will need. You know, so we're kind of doing step by step, and now we're at the kind of final step of this. Okay, is that clear? Okay. All right. So now, so effectively, what we want to do here is to think about the R&D and the endogenous productivity dynamics, right? And this will be a model. What we think about is the firm's endogenous innovation. Okay, so here we're going to settle a model that's within the firm, their investment will be responding to some external changes, such that their productivity will not be exogenously moving. Right? As I already said, there's really no reason you should think about. There's no reason you should think about the omega IT is actually only depend on omega IT minus 1, right? So the omega t plus 1 will be omega IT. And here, you should be free to put in much of the choices that you think firms will be making, right? So one easy choice will be just think about maybe the R&D decision, right? You can think about anything else. Maybe you know, you think about exporting will be affecting its productivity too by like learning by exporting. So you can have multiple choices there. Okay, but the question is, how do you write down the decisions itself, right? That will depend on the micro-founded behavior. So what you need to do is also to have some kind of decision rules, which usually, let's start with simple, right? Think about this as discrete decisions, depend on the omega it and some other state variables. Maybe dit minus 1, maybe eit minus 1. Okay, that's the structure you would expect to see motivated from a standard model. But the key thing is to say this is not ad hoc, right? This will be coming from an optimization problem. Okay, that's the roadmap. Okay, so don't get overwhelmed by the details. Basically what you should look at is that it'll be a standard. Sorry. It will be a standard production function estimation approach, supplemented with this decision rule. That's what you need to estimate. Okay. Okay. Now let me use the limited time, just jump over a few things to tell you about the framework. Okay. So the first part will be related to this. Okay. The first part is, again, let's actually work out the micro foundation for revenue production function. Okay. So here I'm taking a little bit different strategy to think about. Instead of starting with a production function, we can start with a cost function. That's not that much different at the end of the day. Okay. So think about, you have a short-run cost function. This is a log marginal cost, and it will depend on the capital stock and the wage rate that firm's been facing and the productivity XIT. Okay. This is very easily motivated. If you have a Cobb-Douglas production function where the capital is not easily movable, it's quasi-fixed, then you will have such a cost function by only changing labor. Is that clear? Right? Okay. So you have this short-run cost function, and then with the capital being the capital stock, K the capital stock, and the WT will be the variable input prices, and this is productivity. Okay. So there are two things will make these log marginal costs differ across the firms. One is that you have different size. The other is you have different productivity. Okay. Okay. Now just let's do the trick for the CES of the Clayton-Gridikis and DeLoca paper, okay, that you have seen. Let's make sure that the demand is going to be a CES. Okay. And now we can have two separate demand because we'll be looking at a firm that will be doing the export decision. So you have a domestic demand curve, which very much just like the previous setup, depend on the industry demand quantity, the market size, your own price versus the industry price, subject to the constant elasticity eta d. Okay, you could also have an export market demand, which is pretty much the same, subject to the same demand equation. Okay, and with a firm-specific demand shock in the export market. That's the CIT. Okay, that's very much the DeLoca setup. Is that clear? Okay. So now I'm going to combine this again with this. Okay. This is surprisingly simple. Why? Because under the CS demand, what's the markup? I just mentioned why actually I hope people don't like it. So what's the markup? It's constant markup, right? So putting a constant markup on this C, you get your revenue, right? So that's exactly what you can do. Is basically you use this CS combined with the cost and the constant markup, you can write your revenue equation. These are the two revenue equations you will be having. This is the constant markup, right? Okay. So now, again, as I said, this will be, you can estimate this in very much standard production function estimation. Okay, a little bit more tricky, but not that different. Okay, you'll be able to estimate this using production function estimation. And once you do that, you can actually transform this very straightforwardly into a profit equation, into a profit function. Why? Because again, you have constant markup, right? So a fixed share of your revenue goes to the profit. Okay, you can allow the elasticity to be different across different markets, but nevertheless, fixed share of that is going to the profit. Okay, is that clear? Okay, all right. So this is but there's one more important piece, which here is exactly what I said. Other than the standard revenue productivity equation, right? The important thing is you allow the productivity to be endogenously depend on these lag decision variables. Here it does include your R&D decision and also your export decision, right? So these are your R&D decision, which is discrete, and these are your export decision. Both going to affecting your future productivity change through the learning by investing or learning by exporting. Okay, and this will be the equation you can combine with these two equations to estimating a first stage, just like how you estimate ACF or like Early-Pickus. Okay, all right, is that all right? So now I'm going to skip all the details of this, okay, because we know how to do that already. The more tricky part is that once you estimate this and back out your productivity and also your profit here, how we map everything here into a decision rule. Okay, that's the second part. We know how to do that already, right? I've told you how to do that. Now the question is how we map this into a decision rule. And that will actually set you up into a dynamic model, because we know that fundamentally R&D is going to be a dynamic decision, right? So here is what you're going to think about is that by doing dynamics, you have to think about the timing, right? So basically, you have to have the firms that's going to observe some random fixed cost of exporting and the sunk cost of exporting that then they're going to make an export decision. And then they observe the random fixed cost of R&D and the sunk cost of R&D, then going to make the R&D decision. Okay, so this dynamic problem is going to microform the decision rule for us. Okay, that'll be the second stage. Okay, so here's the second stage. Okay, now you see a bunch of value function floating around. Basically, what it does is to think about if you have this is basically the value function before any shocks is realized, right? So once we estimate Early-Pickus and all the ACF trick here, we know what profit looks like. We don't need to worry about it, right? Once we know the profit looks like, we can write it as if these are treated as known, and all you need to decide on is whether do I want to do exporting, right? If I'm doing exporting, I'm paying this amount of cost, but I'm getting my value of the future to be an exporter. If I don't do exporting, I'm getting my value to be a domestic guy. Okay, so these are the VITE and the VITD. Okay, and how to think about the VITE? This will be the value of the firm that given my optimal R&D decision, right? And how does R&D affect my future value? That's going to affect my future productivity, right? That's SIT plus 1. And how? That's coming from your first stage estimation. You're going to plug in your estimation here, right, into here to calculate your future value, right? And then you're going to use, if you don't do it, then this G is going to just going to be exogenously evolving, and that will be your another value that you will be plugging in. Okay, so that's how you combine the first stage and the second stage. So the first stage using all the techniques we have learned to estimate this process, right, as well as the profit function. The second stage, what you do is to write down this value function explicitly and to estimate all the costs. based on these discrete choices. That is going to give you this decision rule. Okay, that's the kind of the sketch of the typically, if you want to do policy analysis about how does the government policy affect firm decision, right? Which in turn enter into the firm's productivity process. That's the kind of decision you have to solve out here. Okay, I'm not going to go into the details, but I'm trying to just give you a flavor of what this type of problem in general looks like. If you're interested, there are a lot of slides. There are also kind of more basic slides that talk about how to estimate this type of model. I've included them into a whole package. I'm going to just distribute the slides, and you can take a read.